All right, guys, so we're talking about the average value theorem today. Let's go ahead and begin. What I'd like you guys to do is I'm going to give you guys about maybe a minute or two. I want you to stare at this, read the question, see if you can figure out the answer. I'll give you like 2 minutes-ish. In here. So Dario went ahead and helped us out here with that. He told us the answer was 4. So I'm going to ask Dario how he figured that out. What did you do, Dario? There you go. So basically, we just need to find out how much do we need overall. And the answer is 2 plus 3 plus 4 plus 5 plus 6, and that's 20, right? You just add it all up. And you want to know how much you need to produce each year just to keep up with that? Then you need to start by producing, you need to divide that by 5 for 5 years. And that means every year you should be producing 4, whatever the resource is, right?
You could always just produce 2 in 2014 and 3 in 2015.
Yeah, I see that. I was going for an average, like across the board, but yeah.
You should have mixed it up because it looks like this is an increasing trend line. We're all going to die when next year we require yet more of unspecified resource.
Yeah, maybe we would have. So it's good that we started this year producing extra. All right. Anyway, so check this out, guys. I'm gonna draw a line at that value that Dario found right there. Okay. And I want you guys to notice something. I want you guys to have 3 takeaways from this slide. Look at this amount that's over what we need, right? Right? Compare that to what we were at the blank space there, right? They're identical. And so here's what we're doing today. We're calculating something known as the average value, and Dario just did that, and a few of you other people out here just did that as well. Now, takeaway number 1 is that if you draw a horizontal line at that number, the amount of area that's over that average bar should fill in perfectly the missing area underneath of it. Okay? So that's one takeaway I want you guys to have. The other takeaway is this. It's an average y value. So there's your other takeaway. So it's an average y value. It's the average height of your bars there, and so that's your second takeaway. So we have 2 takeaways so far. It's about matching area above and below, and it's an average y value. Here's your third one. Your third one is what about when you're dealing with a smooth curve though? Not just rectangles for area, but what if you're dealing with a smooth curve like but let's say it was like this, and this whole thing was filled in with orange. How would I add up all the rectangles? You would integrate. There you go. So that 20 that Dario got here, that 20 that he got, we're going to get that in calculus by integrating from our first point to our last point. That's how we're going to get that total. Once we get that total, we're going to divide by 5. Now, where did the 5 come from? 5 minus 0, the distance, right? 5 take away 0. That leads us to our formula for the average value theorem. We're not going to write it like that, though. We're going to write it like this. This represents the sum, the total area under the curve. And if you divide that by the distance at the bottom, b minus a, then that will tell you the average y value. So this is the sum of all your y values divided by how many y values you have gives you the average y value, okay? So that's the idea. So 3 takeaways, all right? Takeaway 1, the average value gives you a horizontal bar where the area above should fill in the area missing below. Second takeaway, it's an average y value, the average height of the rectangles. Third takeaway is our formula. Add all your y's together and divide by the base. Okay? So that's what we're doing today. So we're going to actually look at a calculus question. So now I'm going to throw another question out here to you, and I'll just take a volunteer for this one. Where should I draw a horizontal bar so that the area above that bar would fill in perfectly the missing area below it. If you feel like you can do that, come on up and draw me a line. Okay.
I can make a guess.
Yeah, that's all we're doing. We're not going to be precise. I think he was. I'm going to go with Brody. Go ahead.
I could also make a bunch of trapezoids and try it that way.
No. We're not going to be that precise. We'll get there. We are going to do that today, but not yet.
And I can see them. I can see them in the curves. So if we've got this amount, right? And we got
he's
these amounts. And I got these amounts. So I'm not gonna precisely. I'm just gonna like think.
Okay.
Yeah.
Okay. Thank you, sir.
That's how you do math.
That's how you. Thank you. All right. Now let me ask you guys a question. If you guys were to take this area that's above the brown line over here and here, do you feel like that would fill in this area perfectly? Is that a good match? What do we have too much of? We got too much green, so what should we do? What should we do? Raise the bar. So someone else want to come try a shot at it? Marcos, come on up. That's all right. We're just guessing.
Is it on the pen already?
Yeah, I think it is.
No, that's not straight. Hold on. It's on. It's kind of delayed. That's why I put mine.
All right. Let's see if he's got a better match this time. Ready? So here's my area above. All this here. That's all right. That's all right. And then here's my area below. Do you feel like if you were to take all this sand up here and dump it into that hole, would it be a good match? Too much sand or too little sand? Too much sand. Okay, so let's try one more guess here. So come on up, Jen. You show us where the bar should go.
Okay. Not too much top.
Oh, that was me. That was me. I'm sorry. I sat on my keyboard. All right, there you go.
What?
All right.
Not enough top.
Thank you, Jennifer. Let's see.
Some of it could fit in there, and then some could fit right there.
All right, let's check it out. This, and this. No, it's got to be a bar. A bar. What do you guys think? Do you think that green area would sufficiently fill in the orange area?
Too much.
What? What would you do?
I would do like a diagonal line.
Oh, it's got to be bar. It's got to be. Yeah, she was thinking that too. I would say Jennifer's pretty close. It's hard to get this thing exactly right. Okay. I would maybe if I had to drop, I would drop it a hair, right? But you guys have the idea. I just wanted you guys to run through this exercise a few times to get used to it. And think of it as like the stuff that's over the line is like sand, and the stuff below it is like you want to fill that in the hole, right? So that you end up with a level ground. All right. So that means that based on Jennifer's estimation here, she would say that her average value is about what? Y equals what? 15? Let's see how good her estimation was. Here's what I'm going to do what Brody was trying to do initially. We can actually get a very precise answer if we know some stuff, if we know the actual area under the curve. So I'm going to tell you the area under the curve is 18. What did I say? Oh, you don't need the zeros. Zero's nothing. All right. So, can somebody tell me the exact area or the exact average value now? I'm going to pause for a minute and let you guys think. You probably need a calculator for this.
No. I don't need
I know I do. Think so?
I do.
You guys can get an answer to the thousandths if you wanted to. You can be very precise.
Wait, there's a decimal.
I know. It's whatever.
6.5.
I got 13.4.
Now you're reciting pi.
15.000.
Okay. Now I gave you guys a formula in the last slide, right? We decided the average value is the sum of all your y values divided by the distance. So what is my b on this problem? What's my a? Well, maybe that's why Austin was saying 15. I meant to have -1 here because look at your picture over there.
Yeah,
Sorry.
I knew it was -1.
So
You made a
sorry.
boo-boo.
I did. All right. So
111.
hold on. Let me finish my thought here. So this is 1 over 11. So the base from here to here is 1 over 11. And then this is, what's the integral from -1 to 10? 180, right? So if you multiply those, you get, so maybe, Austin, is that why you got 15?
Yes.
Okay, well, I had a boo-boo. So let's see. It's going to be 16 point, what? I have to do it again. I lost it.
363636.
Thank you. So there. Now she said 15, Jennifer, right? She's pretty darn close. And we thought maybe you'd have to lower it. But I guess according to this, you have to raise it. It's possible that my graph is not scaled perfectly. But anyway. So that's what we call the average value theorem. All right. So you guys may have noticed something. You may have noticed that that sounds an awful lot like something we've already learned this year, the mean value theorem. And that's confusing because I thought an average was a mean. And well, that's fine, but those are different theorems, and we need to make sure we understand the difference. But I also want you to see the similarities. They actually have some things in common, a very interesting thing in common. But we'll get there. So for now, let's review the mean value theorem. The mean value theorem is one of those theorems that says that if you have a continuous function and it's differentiable, somewhere along that curve, the instantaneous rate of change is equal to the average rate of change. In other words, the tangent line is parallel to the secant line. It's an elephant. They bought one to pick up trash on campus. All right, now it's an elephant. We're going to compare and contrast these theorems right now, and you guys are going to fill this in on your notes. But yes, man?
After we go over this, like, could you help me with just the limit steps?
Sure, man. Sure thing. All right. I'm going to go through like an example, and when we start student practice, I'll pop over and help you out. All right. So first of all, guys, let's talk about this. So mean value theorem, guys, helps you deal with the average. What? Good. It's the average rate of change, which you could also just technically say slope, but it's average rate of change. All right. Whereas the average value theorem doesn't tell you the average slope. It tells you the average what? No. Shh, guys. The average y value. The average height. So there's one difference and similarity. They're both averages, right? But the average value theorem tells you the average height of your function. The mean value theorem tells you the average slope of your function. Okay, those are different ideas, right? And we've already seen the difference in their formulas, right? We know that this is the formula for the Dumbo. That's the formula for the mean value theorem, and this is the formula for the average value theorem. So as you guys can see, mean value theorem has to do with derivatives. Average value theorem has to do with integrals. So there's another difference, right? The last thing I would encourage you guys to have down in your paper is the geometry of these things. So like I would draw this picture to represent the mean value theorem. It's where your tangent line and your secant line are parallel. Okay? Whereas for the average value theorem, it's about drawing a horizontal line so that the area above matches the area below. Okay, so there's the geometry of the matter. So we want to make sure we see this from a concept, an algebra, and a geometry perspective here, because you need to recognize and understand them from all three angles there. So I'll leave that up there for a little bit. Value theorem and mean value theorem. Now, here's the next part. This is a really cool part. It turns out that these guys are actually brothers and sisters, or cousins, if you will, the mean value theorem and average value theorem, and they're related by the same parent. Their parent is the fundamental theorem of calculus. So, you can't, well, you see, Isaac, when an integral loves an antiderivative very much. Okay, so remember the fundamental theorem of calculus? You take the integral of a derivative from a to b. The integral of f prime would be f, and you plug in the b and the a and you subtract them, right? Okay, now watch this. If we divide both sides by b minus a, watch what we get. What is the left side? That's your AVT. What's the right side?
MVT.
I'll be darned.
So they're the same.
They actually are, but there's a very important difference to see. Okay? Here's the difference. Ready? The average value of your derivative is the average rate of change of the original function. I'll say it again. The average value, the average y value, the average output of your derivative is the average rate of change of your original. Okay? Now, I could reword this. The average value of f prime of x, that means the average rate of change. I could reword the average rate of change of f as the average value of the slope. They are the same thing. So when you're doing your FRQs this week in your homework, I put two types of questions in there. Sometimes it says find the average value. Sometimes it says find the average rate of change. Based on the function, you need to know when do you use each theorem. Okay? So if I give you f and I ask you to find the average rate of change, you're doing this. If I give you this and I ask you to find the average value, you're doing this, but they're really finding the same thing. Okay, it depends on what you're given. The average value of that is the average rate of change of that. Okay, so there we go. So now we're going to actually do the math here. So did I print this for you? I did not print it? Okay, go ahead and copy it down. So guys, I'm asking you to find the average value of this function. I want to find the average height or the average distance that this function has from the x-axis, okay? That's what this means. So now I would say if you could set up your problem, you've learned the new thing for today, okay? The problem is you're remembering the old stuff to finish the problem, okay? But setting it up is the new thing. So let's set it up. The formula goes like this. It's 1 over b minus a. So what's the b value? Good. And what's the a value? Notice your double negatives, right? I'm subtracting a negative pi over 6, right? b minus a. Now my function is how do you know it's the AVT? It's right here. Yeah, if they said average rate of change, that would be MVT. All right, so there's that. Now, you're going to put your A's and B's here as well, right? Sorry, I'm using the green again. I was asked not to. That's weird. There we go. Ha! Victory. All right. So, so now here's where we get to do some memory. Okay. First of all, this is going to simplify to be 1 over pi over 2 plus pi over 6, right? Let's just do that. But now we're going to actually integrate this thing. Now this is the part I see a lot of students skipping, okay? A lot of people are just doing, don't write this. A lot of students are just doing this. They're dropping the squiggle and they're putting brackets and they're good. That's wrong. You drop the squiggle and put the brackets if you've integrated. And so on your student practice today, don't forget your integration. So what is the integral of 2 sine x? Good, but there's a 2, right? So it's negative 2 cosine x, because the integral of sine is negative cosine. And since there's a 2, it's negative 2 cosine x, right? So don't skip out on that. Don't forget to do your integration, for goodness sake. Okay, so the next thing that we're going to do is we're going to apply the fundamental theorem of calculus here. So I got silly there. Hold on a minute. Okay, so we have negative 2 cosine of pi over 2 minus negative 2 cosine of negative pi over 6. Uh-huh.
Oh, they asked how come the pi over 2 plus pi over 6 becomes positive in the
Double negatives. If you look at those step right before it, it's minus a negative, right? Nate, I'm surprised you didn't know that. I'm really disappointed.
I know. Sorry.
Okay, so now we get to do some trigonometry. Okay, guys, please stop cheering. I understand this is exciting, but I mean, I need to be able to teach. I appreciate your enthusiasm. Okay, here we go. So, unit circle. Pi over 2 is up here, right? And cosine is an x value. It's 0. So, this is just basically going to end up being 0, so we could get rid of that, kind of, right? Now, this is going to end up being a plus. You guys good with that? Because of the double negatives there? Okay, now let's do the cosine. So, cosine of negative pi over 6. Where's negative pi over 6 located? Bottom left, right? Like right about here?
Yeah.
What's the x value for that point? No, it's below. No. Radical 3 over 2, yeah. So this one's going to be radical 3 over 2.
Wouldn't it be 2 times 2 times radical 3 over 2?
Why?
Because it's 2 cosine.
Oh, thank you, guys. Alyssa pointed something out for me. There's a 2 here.
And then it cancels.
Because this was 2 cosine. Thank you, Alyssa. I'm giving you a point for that. That was helpful. I totally missed that. All right. Joking. Okay, here we go. Pi over 2 plus pi over 6. By the way, guys, if this was an FRQ, I would have stopped even sooner than this. I would have stopped up here. Because once you've plugged in those numbers, your calculus is done. That's the fundamental theorem of calculus. After that, it's just trigonometry and algebra. So I would stop right there if it was an FRQ. Okay? There's no sense in getting things wrong after that. But I still want to review this stuff with you because you might need it for multiple choice stuff. So now we've got radical 3 here. We're going to multiply and we're going to get this. We're almost there, but we don't like improper fractions. Do you guys remember how we handle improper fractions? Kind of, but how do you do that? Multiply by what? Multiply by the little denominators. What would be a good denominator to multiply by? The 6, because the 6 will cancel the 6 and the 2, right? So I'm going to multiply by 6 times 6 times 6. No evil reference intended. 2 goes into 6 3 times. And then these cancel. And 3 pi plus 1 pi is final answer. That's the average value. That's the average height of your function.
Right.
All right, so I'm going to put one up for you. Now, yours isn't going to be a crazy trig problem or anything like that. Yours is actually very simple, but please, before you get rid of your squiggly, what do you need to do? Integrate it.
What is this
Average y value. Average y value.
I know, I don't like it.
Okay, there you go. Go. Don't waste time. Isaac, what's my setup here?
You're going to be the 1 over b minus a, so it's going to be 1 over 2 plus 3.
Good.
And then you got the 2x.
Good. And then we need our limits on here too, right?
Yeah.
Okay, good. So the next thing is, Jacob, I want you to help me fill something in here. What goes here? Good. So I saw you. I warned you guys, so you guys integrated. I had a lot of people not doing that in the last block, so don't forget to integrate. And then from there, we plug stuff in, right? So it's going to be 2 squared minus negative 3 squared, which is going to be 1/5 times 4 minus 9, which is 5, negative 5. And so negative 1. And that represents the average height of the function, the average distance from the x-axis, so to speak. Yeah.
So,
Oh, I never talked to you about your problem. I forgot. But anyway, go ahead.
so like, the 1/5 is different just because.
Now, guys, I don't see the questions presented like that very often on AP materials, but I do see them presented as tables. All right? So go ahead and find this table on your notes, and let's go ahead and do this together. Now, when you're dealing with tables, the beginning is the same. You still set it up. It's going to be 1 over b minus a. What's my b? And my a? Good. And we're dealing with the function f of x, so I'm going to put f of x right here. And there's your average value. So there's your setup. Now here's the deal though. When you're doing a table, you can't integrate it because you don't actually have a function. All you do is you have specific values. So the only way to find an integral with a table is by estimating the integral by doing left, right, trapezoid, or midpoint. Okay? And that's what we're going to do here is we're going to do a trapezoid. Okay? So for the trapezoid, we start by finding our heights, right? 3, 3, 3, 1. These are my bases. So my first trapezoid will be these two with that height. So it's going to be 3 over 2 times 7 plus 6. My next trapezoid is going to be these two with that height. Next one is these two bases with that height. And my last one will be these two bases with that height. And then we're going to go ahead and calculate all those. So for the first one, I get 39 halves. For the next one, I get 42 halves. And I'm going to leave it as a fraction, just in case they don't all reduce. And I need to add them anyway. So 15 and 5 makes 45. And then 13. So yeah, there's a couple in here that aren't going to reduce. So I'm just going to go ahead and leave them all as fractions. We'll add them up.
I got 139.
Thank you. I appreciate it. So if we add them all up, we get 139 over 2. right? So now, then this formula becomes 1 over 10, right, from here. And then this becomes 139 over 2. So this is an estimation of the area under the curve. So that means our average value is going to be the average of the estimated area. Yeah, little brain issue there. And then we go ahead and multiply straight across, and we get 139 over 20 would be our average value. And if you do this, you're going to end up with something like 6.96, I think. And I mean, just compare that. Look at your y values. Wouldn't you guys say that 6.96 is a pretty decent y value average for all those y values? So Angelisa said, why don't we just find the average of the y's? Now, there's a reason for it. Okay, that's not what she meant, but it's a good question. So let me ask you this. Why can't I just add up all the y values and divide by 5? Does anybody have a good answer for why that won't work?
Because we don't know what the y values are.
That's partially right, but a little bit more depth. Yeah? Okay, yeah, so you definitely have to follow the rules, right? But still looking for a little bit more. Yeah?
This is the average line, not really where the line's supposed to go.
I'm not sure about that one. But here's why. Because this is 7 and 6, right? But what if this was a 5 instead of a 3? Right? That means that this just became a wider rectangle, and that y value just became more powerful. Do you see that? So the wider your base, the more influential those y values are. And so depending on how wide or skinny they are, it's not like this is just 7, 6, 8, 7, and 6. These are y values that we're stretching them out over a certain distance. So the more distance you stretch them out over, the more influence they have on the average. So it's not really just isolated y values. So I don't know if that made sense, but that was my attempt to explain it. All right, here you guys go. You guys are going to do a right-hand Riemann sum to find the average value. You're not doing a trapezoid. You're doing a right-hand Riemann sum to find the average value. I'm going to show you guys how to do this just in case you didn't get your answer. But if I get up quiet right now real quick. So I did see a couple people struggling here, so make sure you know how to get your limits. Your limits are the first x value and the last x value. And those are also the numbers that go here for your average value. Okay? Now, the integral, we were told we're going to be estimating using a right-handed Riemann sum, and so here's where our review comes into play. All right? So we find the bases of our rectangles first. And with right-handed Riemann sums, we start here. That's our height times base. Height times base. Height times base. Height times base. We don't use the last one. And so we have 8, 5, 15, 4. And if we add all those together, we get 32. Which if you multiply by 1/10, you get 3.2. Okay? So there's your average value for that function. That's what FRQs usually look like. Okay, that for these average value theorems. I don't see them giving a whole lot where you actually have to do the integral like we did at first, but we definitely need to review integration in our class. You guys need a little help with that. It's been a while. So we'll get there. Let's go ahead and do one more example here. Now, you don't have to write this one down, you guys. I'll leave it up to you. If you want to write down this problem, you can. You do have a homework problem where I ask you to do one on a calculator. But really, I'm just doing it so it can be on the video. So if you guys get stuck on that one in your homework, you can pop open the video and follow the steps again. So I want to show you guys how to calculate the average value using a calculator. So before we begin, and by the way, anytime on an FRQ, it's a calculator FRQ, you have to give them something. You can't just put the answer. You could, I know, because you do it all in the calculator, right? But if you just put the answer, you get nothing. You would have to give them the setup. So for instance, you would have to do this. If you do that and then you put the answer, then you're good. If you just put the answer, they won't give you anything. So they want to see that you actually know the calculus and you didn't just peek over your neighbor's shoulder. All right? So it's really quite simple, you guys, because you're literally just going to be typing this in exactly as it appears. Just a few suggestions as we go. It's 1 over 2, right? Now for that fraction in the front, you're going to want to put that. Can I have quiet, please? Can I have quiet, please? All right, so for that fraction in the front, you want to have that in parentheses. If you don't do that, you're going to get the wrong answer. Okay? Then the next thing you do is you push math, and you're going to scroll down to number 9 where it says, or you could just press 9. Now, I have an older version of a calculator, so unfortunately it will not look like an integral. It says FN, and then I got to type in the code. But most of you guys have the newer ones. Pretty easy to see how to type it in. But if you have one like mine, you just do what I do. For these ones, to get the integral, you type the function in first, so it's going to be e to the x, close parentheses, and then x squared, right? E to the x times x squared. After that, you do comma, and you tell it what is your variable of integration. It's x. That's what dx is. It tells you what variable we're integrating. Comma, and then you do your limit, starting with your lowest and ending with your highest. So -1, comma 1, close parentheses, enter, and there's the average value. So it does it for you, but you do have to at least show your setup. You do at least have to show your setup whenever you do your work. Okay? So that's it. That's the end of our lesson for today. We'll call it a day.
Call it a day. Let's call it a